So we're going to start where we finished last time. So last time we started with the example that you see on the left. Find the eigenvalues of this matrix for -3, 6, -7. And so the procedure is where it says up here, you find a polynomial, and the polynomial comes from a determinant, a minus lambda I. So we take a minus lambda I. So it's a minus lambda. Remember that I stands for the identity. One's on the diagonal. So when you put them together, what you're really doing is it's the matrix A, where you've subtracted lambda on the diagonal. Take that determinant, and that leads to a polynomial. And then what we're really after is when we're looking for the eigenvalues, is we're after the roots. So we say, great, our eigenvalues are 2 and -5. Now, simultaneous to this, there's this other problem. It says, use the method of elimination, which is the variation of Cramer's rule on the system. X prime equals, x1 prime, is 4x1 minus 3x2. x2 prime is 6x1 minus 7x2. And now there's a reason we want to do these side by side, because if you look at these coefficients, 4 minus 3, 6 minus 7, it's the coefficients you see here. That's not a coincidence. That's not a coincidence. And indeed, you could rewrite this. This is like, this could be rewritten as x1, x2 prime is equal to 4 minus 3, 6 minus 7, x1, x2. So in particular, it's the same matrix. And so you say, well, should we expect to see a similar process? Well, what happens? Here we subtract the x1 prime and the x2 prime across to get a new set of equations where everything's on one side. We rewrite it in our notation where we have d standing for derivative. And we solve for x1. And you'll say, hey, look at this matrix. 4 minus d minus 3, 6 minus 7 minus d. It's essentially the same thing here. It's just you swap d's and lambdas. And so in particular, when you go through and you say, aha, we get a differential equation, we turn into an algebra problem. It's the same algebra problem, just swapping r's and lambdas. Now that's not a coincidence, because really what's happening is it's the same ideas in the background. So this idea about using eigenvalues is not that far off from what we did when we did method of elimination for very simple systems. Okay, but eigenvalues are only half of the story. Because with eigenvalues come eigenvectors. So how do we find those? So we should talk about that. So finding eigenvectors. Now, you might say, wait, can you remind me what an eigenvector is? Yeah, I can do that. So an eigenvector is something where a times v equals lambda times v. And in particular, when we talk about the vector, that's the v part. So we're looking for this special vector v, such that when we multiply a times v, it's a multiple of itself. Okay, so we say, all right, we know how to find these eigenvalues. It's about solving for roots of polynomials. How do we do it? Well, here's a very general approach. We know that if a times v equals lambda v, then really what we can look at is a minus lambda I. Because what this is telling you is says, oh, I'm trying to solve a minus lambda I times v equals 0. So this is saying, hey, set up the system of equations that corresponds to this problem. And now you do your row reduction. The same kind of row reduction we talked about when we were finding inverses. So in other words, we can do things such as swap rows, multiply a row by a non-zero, add a multiple of one row to another, and you clean up as much as possible. Now you won't be able to go all the way. You're guaranteed that you're going to have at least a row of all zeros on the bottom. Now the reason that you're guaranteed is because this matrix A minus lambda I is, you might call it deficient, but we're counting on the fact that you can't have full rank. Now, rank is a technical term, but basically, we're counting on the fact that there has to be redundancy. Well, what you're really doing when you do this kind of computation is you really just have a system of equations. You write out the system of equations, you find the linear relationships among the entries, and that translates into vectors. And of course, they're not unique, because I can always scale. So you scale to make them look pretty. Now that's finding eigenvectors in general. But our class, we're focusing on 2x2s. So maybe once in a while we might have to do a 3x3. For that, well, we can always ask a computer. How do you do 2x2s? So for 2x2s, it's actually pretty quick. Here's what happens. For 2x2 matrices, you start with A minus lambda I. Okay. It's some matrix. And now we say eigenvector is either beta minus alpha, so it's sort of reverse the order here, change the sign on 1, or it's delta minus gamma. Just pick one of those. And you're done. So if you can remember this, you'll be in good shape. All right. Let's do an example. So we'll have this for reference while we work our example. Find the eigenvectors of A equals 4, 3, 6, negative 7. Using the eigenvalues previously found. So do you remember what those were? Yeah, 2 and negative 5. So those were the ones we previously found. So we say, great. Lambda equals 2. Lambda equals negative 5. So let's start with 2. So I'm going to look at the matrix A minus 2I. What does that matrix look like? What are the entries? 2. Negative 3, because the only thing that changes is the diagonals, because 2I only has entries on the diagonals. So it's A where you subtract 2 on the diagonals. All right, what's the entry down in this corner? 6 and negative 9. Okay, that's A minus 2I. Now, if we believe this is true, can you give me an eigenvector? So, if we just see, this is our alpha beta. This says beta minus alpha. So negative 3, negative 2. Of course, we can clean that up. We can scale it. Is there anything nice to scale by? Yeah, negative 1, 3, 2. Or we could have gone downstairs. So in that case, thinking the second row being gamma delta, 6, negative 9. Well, that would have been negative 9, negative 6. Well, what could we have scaled by here? Negative 1/3, and we would have ended up with 3, 2. Whoa, did I just blow your mind? What? Okay, so this 3, 2, that is our eigenvector for lambda equals 2. All right, let's pause for a few seconds and just point a couple things out. How could I verify that this is in fact the eigenvector for 2? Plug it in. How do I plug it in to verify? What's a special relationship that eigenvectors have? If it helps, I'll move this over. If it helps, I'll start pointing to it. I'll now point to it with two things. I'll now circle it. I'll now look at you with puppy dog eyes. Please. All right, I'm not very good at that one. All right, so the point here is you know something's an eigenvector if when you multiply it by the original matrix, you end up scaling it. So let's just see if that actually works. So 4 minus 3, 6 minus 7 times 3, 2. All right, you'd have 12, all right, subtract 6. 12 subtract 6, also known as 6. 18 subtract 14. It's 4. And notice that this is 2 times 3, 2. So when I take AV, it's lambda V. So we know it worked. All right, so this is the you see the relationships. Now, if we go back and say, well, how does it work in this setting? Well, the idea is to say, okay, so here's our A minus lambda I. So the other way to think about the problem, if you don't think about the shortcut, is to say, look, I'm looking for some vector that does this. 2 minus 3, 6 minus 9, AB equals 0, 0, because that's what we're after. This becomes, of course, 2a minus 3b equals 0, and 6a minus 9b equals 0. And we have two equations and two unknowns. Now, this notation just says, oh, there's a shortcut which keeps track of your equations in a tabular form, table format. But really, you have two equations, two unknowns. If we were to solve these two equations, two unknowns, what would you notice? What do you notice about these two equations? They're scalar multiples. In other words, there's redundancies. It has to happen for eigenvectors to work. So you say, it's really not two equations, two unknowns. It's really one equation, one unknown. So I have to find some relationship between A and B where 2a minus 3b equals 0. So you could say something like, oh, that says B equals 2/3 A, right? Because I could move the 3b, divide by 3. And then we would say, well, that tells us our AB looks like A and 2/3 A. So the A is just arbitrary. You pull it out, you get A, 1, and 2/3. And now you have an eigenvector. Of course, you can scale it because, like, I don't like fractions. So multiply by 3. You get your 3, 2. So this process of setting up a system of equations is what's going on here. This process is basically saying, hey, I already see that one of your equations is redundant. And then it's like, oh, if I want 2a minus 3b to equal 0, we'll just say a equals minus 3 and b equals 2. So that's what happened. All right, now that's only the lambda equals 2. Well, lambda equals -5, we'll do a little bit quicker. Okay, so now that we've done lambda equals 2 to a very high degree, all right, a minus 5i is a plus 5i. What does the matrix look like? Nine, -3, 6, -2. Okay, so now we're looking at it. Now in the back of your mind, you can think about, you're saying, I need some vector so that when I multiply here, I get 0, 0. Right? This is sort of in the back of your mind. Can you spot the vector that does that? Can you see a vector that does that? If not, go back to the rules. Doesn't have to be the prettiest vector to start with. Anyone see a vector that'll work? 1, 3. You can always check, right? 1, 3. 9 minus 9 is 0. 6 minus 6 is 0. So that works. You could, of course, also said, oh, all right, I'm going to take my beta, -3, minus alpha is -9, and that would have been your -3 minus 9. Well, I can scale by -1/3 and get 1, 3. Okay, so we can find eigenvectors, and we know how to find eigenvalues, but then there's one other part. I said use this to give the general form for solutions of x prime equals ax. Now this requires you to remember what we talked about last time. So last time, remember we said, aha, our guess is that solutions look like v e to the lambda x. Lambda t. Lambda is your eigenvalue. V is your eigenvector. So we have eigenvalue, eigenvector pairs. So these are solutions. That's why we went through all this work. So each one of these pairs represents a solution. So in particular, if we start, where's our good eigenvector? Here's a good eigenvector. So e to the 2t, the 2 coming from the eigenvalue, 3, 2, is a solution. Come over here, we have e to the minus 5t, 1, 3, is a solution. Eigenvalue, eigenvector, eigenvalue, eigenvector. Now, if we want the general form, what do we do? Throw in some nice arbitrary constants and add them. And we're done. So this is all about finding our solutions to x prime equals ax. Once we have eigenvalues and eigenvectors, we get our pieces, and we add our pieces together. Now, fun fact, as long as your eigenvalues and eigenvectors are distinct, these are going to be linearly independent. In the words of the Wronskian, the Wronskian's non-zero. So, to summarize, here's the game plan. If we want to solve x prime equals ax, step 1, find the eigenvalues of A. Now, if it's A is an n by n matrix, you'll have n of them. So 2 by 2, you'll get 2 of them. If possible, find your eigenvectors. Now you might say, is it always possible? And then there's a nope. That's for a later discussion. All right. But that's not for today. Today it will be possible. So, find the eigenvalues. Find the eigenvectors. Then we say, aha, solutions look like e to the eigenvalue t corresponding eigenvector. They're linearly independent, so take a combination and you get your general solution. If you have initial conditions, then what do you do? Use them to solve for c's. Okay, so an example, the kind of example that's very popular on exams. Use the eigenvalue method to solve the system x prime equals 4x plus y, y prime equals 6x minus y, with x of 0 equals 5 and y of 0 equals minus 2. All right, so first off, does this look like an eigenvalue problem right now? It doesn't yet, right? Because what's missing? Matrix. There's no matrix here. So we want to first off say, hey, I can translate this into a different notation. So we're going to think of our vector x, and I know it's hard to see this. This is a bold x. I felt very bold writing it down. But really it's just we're stacking our functions up. So x is xy. So then we have that x prime is the coefficients times x. So what are the coefficients that will go in? 4, 1, 6, negative 1. What is our initial condition? X of 0, it will become a vector. What's the vector? So remember, x is really the stacking our pieces. So this entry will be your x of 0, and this entry will be your y of 0. So 5, negative 2. All right, so this is the restatement. And now we can talk about our various eigenvalue type things. Okay, so step 1, what do we need to do? If it helps, you can read it here. Yeah, find the eigenvalues. Okay, cool. So we're going to take our determinant, 4 minus lambda, 1, 6, minus 1 minus lambda, because we're taking the determinant of a minus lambda I. So we're just subtracting lambda off the diagonal. So, and of course we're saying this equal to 0. So this would become 4 minus lambda, minus 1 minus lambda, subtract 6. We start expanding things out. Let's see, we're going to have a minus 4. Then we have a minus 4 lambda, a plus lambda squared, and a minus 6. Which would be lambda squared minus 3 lambda minus 10. Does this factor?
Yes.
It does factor. Minus 5 plus 2, right? It's always good to check. Lambda squared, 2 lambda minus 5 lambda is minus 3 lambda, and minus 10. So what are the eigenvalues? Negative 2 and 5. Okay, so step 1, done. Step 2, eigenvectors. All right, let's start with lambda equals minus 2. So we're going to look at our a minus lambda I. So essentially, take a look at this matrix. So we'd have 6, 1, 6, 1. Do we see some vector? Can you spot the vector that when you multiply it gives us 0, 0? Yeah, there's a bunch of them that do it. You just need one of them. 1, negative 6 will work. So our eigenvector, well, for negative 2, it's 1, negative 6. Yes? Can you see that process? The logic? Don't worry, you'll get a chance to do one in a few minutes. I know you're like, Steve, I want to do one. It's coming, it's coming. Lambda equals 5. So, think about putting lambda equals 5. 4 minus 5 minus 1, 1. And then you have 6. Minus 1 minus 5 is minus 6. And again, we're looking for some vector that multiplies this, and we get 0, 0. Can we think of a vector that has that nice property? 1, 1. So 1, 1 goes with 5. So step 2 is done. We found our eigenvectors. Okay, we're making great progress. Now, we're ready to do step 3. Now, step 3 just says the general solution. So we say, okay, some constant, e to the minus 2t, 1, negative 6. So I'm grabbing the eigenvalue negative 2, eigenvector 1, negative 6. Some constant, e to the 5t, 1, 1. Are we done? No. What's missing? Initial conditions. So what do we do? Plug in. And we plug in 0. So, say, all right, at t equals 0, we have 5, negative 2. And the nice thing is e to the 0 is 1. So that's a 1, negative 6 plus b 1, 1. Which really is saying we have two equations. One equation, if we read the top entries, says a plus b equals 5. If you read the bottom entries, minus 6a plus b equals negative 2. So what can we do? Yeah, there's lots of things. You know, we could do a subtraction. What comes out? 7a equals 7. So what does it say about a? A equals 1. 1 plus b equals 5, because I'm putting in a equals 1. What does that say about b? B equals 4. All right. So we now know how to satisfy our initial conditions. We say, aha, brilliant. So we have e to the minus 2t, 1, negative 6, plus 4, e to the 5t, 1, 1. And is that our answer? Yes. And why not? We got to go back to where we started. We're the ones who introduced the vectors, not the problem. We've got to say, hey, how did the problem ask the question? That's how we have to go back to. So we've got to go back in terms of the original x and the original y. How do you do it? Well, the vector x is really x, y. That's what we set up here. So we just say, look, if we want the x, you grab the top entries. So grab the top pieces. You'd get e to the minus 2t plus 4e to the 5t. And if you want y, it's the bottom entries. So y would be minus 6 e to the minus 2t plus 4e to the 5t. And now are we done? Yes. Ah, the universal sign of, we did it! Woohoo! All right. So there's the process. You feel comfortable with it? Maybe not. But enough to say, let's try one. Similar idea. Different problem. Use the eigenvalue method to solve the system. X prime equals x plus y. Y prime equals 4x plus y. X of 0 equals 1. And y of 0 equals 10. Well, this is the answer I got. So, in the interest of time, let's just talk through it. We set up as a vector, so it becomes x prime equals 1, 1, 4, 1x. We have a 1, 10, a vector as our initial condition. We solve the eigenvalues and get 3 and negative 1. We work with the eigenvector. So here I take a minus 3i, and I like, 1, 2 will be something that sends this to 0, 0. Here's a minus minus I, so it becomes a plus I, And there 1, -2 is the vector that we need. So, eigenvalues and eigenvectors in hand, we can find the general form. A e to the 3t 1, 2, b e to the minus t 1, -2. It doesn't really matter which one you put first. Then come the initial conditions. So here is what happens at time 0 is a combination of the two eigenvectors. You can solve for your coefficients a and b. So here is our answer in our sort of vector format, and then we pull it apart so that we make sure we get all the points so they don't penalize us for not answering it in the way the question was asked. And lo and behold, we get the answer. All right. So far, so good. Any questions? Everything seems pretty simple. You might worry, might we ever encounter anything which is more complex? Oh, people know where that pun is going. They're like, oh, Steve, oh, I know what you did there. You can have complex eigenvalues. Just like when you solve for roots of polynomials, you can have complex roots. And so we've got to say, well, how do we deal with complex roots? How do we deal with them? Now, because of algebra, we know that when we have real coefficients, which are characteristic polynomials always have real coefficients, our complex roots always come in pairs. So that's like the a plus minus bi. The other thing that happens says, you know, not only do your eigenvalues come in pairs, your eigenvectors come in pairs. And it's the same idea. It's you flip this part with the complex part, the I part. So you take the conjugate of the I part. So here's an example. We have this matrix, 7, 4, -10, -5. And it says, verify that 1 plus 2i is an eigenvalue of this matrix with this eigenvector. Now, we could try to derive it, but why do that when we can just write the answer? And say, look, a verify says we plug things in and make sure it works. So we'll take 7, 4, -10, -5, and we're going to times it by 2 and -3 plus I. Taking the matrix times the vector. If we do that, well, we'll get 7 times 2, which is 14, and plus 4 times -3 plus I. We'll do this a little bit slowly. Yes? But don't. -2 times, 2 times -10 is -20. And then -5 times -3 plus I. Well, all right. The first entry simplifies to what? So 14 minus 12 is 2 plus 4i. The second entry. So -20 plus 15 is -5 minus 5i. Now here's the thing. You might say that I don't see how to pull out a 1 plus 2i because we're not used to that kind of stuff. Well, that's okay. We don't have to. So this was a times v. Now we're going to do lambda times v, which is we're going to take 1 plus 2i and multiply it by 2 times -3 plus I. Okay. Upstairs, well, we get 1 plus 2i times 2. And downstairs, we get 1 plus 2i times -3 plus I. What does it become upstairs? Everyone, I think, can see that. 2 plus 4i. Yes? Now the fun part, downstairs. Okay, let's do the real part. So how can I get a real part? Well, I can take 1 times -3, which is -3, and then I can take 2i times I, which becomes 2i squared. And I squared is a minus. So it's -3 times from the real parts, and then a -2 from the imaginary parts gives you -5. Now, the complex parts, I minus 6i together gives you minus 5i. And now, what do you notice? These match. So that's the verify. That part's done. And then it says, hey, there's an also part. You're not done with this problem. Oh, okay, we spoke too soon. Give the other eigenvalue an eigenvector. But now we say, oh, they told us how to do it. Things occur in conjugate pairs. So if 1 plus 2i is an eigenvalue, what's the other eigenvalue? Yeah, the other eigenvalue has to be 1 minus 2i. Now, since this is associated with the vector 2 minus 3 plus I, what will 1 minus 2i be associated with? 2 minus 3 minus I. Yeah, the punchline is the parts in front of the I change the sign. So that once you have one eigenvalue eigenvector pair, you have the other one for free. But actually, for our purposes, we're going to do things a little bit simpler in some sense. Okay, so our next goal is to talk about solutions from complex eigenvalues. So we have our basic thing. We have x prime equals ax. All the entries are real. So that means what happens if we have a complex eigenvalue? So alpha plus I beta. So in this case, 1 plus 2i. Well, it has an eigenvector. Now, just as we pull apart the real part and the imaginary part for our eigenvalue, we can do it for our eigenvector. And what I mean by that, you see this 2 negative 3 plus I? This can also be written as 2 negative 3 plus I 0, 1. So this first part, 2 negative 3, acts as the A. This second part, 0, 1, acts as the B. So you find your eigenvalue, you find your eigenvector, which will have complex parts, you pull it apart. All right. So then we say, look, we know the idea. E to the eigenvalue t, eigenvector is a solution. It's the same idea that we had before, right? E to the lambda t times v. This is all we're writing down. E to the lambda t times v. That's nothing mysterious. And then we did the same process. Say, oh, we have this fun fact. This expression becomes e to the alpha t cosine beta t, I e to the alpha t sine beta t. So this is de Moivre's formula. And now we're like, we don't want to have complex parts in our answer. So here's the magic. You say, hey, what's going to happen is because things come in conjugate pairs, we have another pair that's almost the same, except the signs change in the middle. And now the great aha, it turns out that you can grab both answers from this expression. So you say, okay, what we'll do is we'll say, what's the real part? So do you remember when we talked about over here multiplying, we said, okay, how do you get the real parts? There's the 1 and the negative 3 and the 2i and the I. So we'll do that again. So here, the a and the e to the alpha t cosine beta t. See, that's a real part, so that's this first piece here. And then you have the imaginary parts. E to the alpha t sine beta t times b. But there's also an I squared. That's where that minus comes from. So that's the real part if you multiply it all out. And then you say, okay, the imaginary parts. Well, the e to the alpha cosine beta t times ib, that's one imaginary part. And then the other imaginary part is the e to the alpha t sine beta t times a. So those are your two solutions. So that's how we get our two solutions when we have complex eigenvalues.